just a few words. Hi, we invited Yechul Shin. Yechul is a postdoc fellow at Seoul National University. He's working with Yong Seong Kook. And Yechul is supported by a Korean Science Fellowship. He's currently visiting us at TUM, and his research focus is on circulation dynamics in, I think, atmosphere and ocean, and particularly the AMOC these days. So yeah, thanks, Yechul, for making the time. Please go ahead.
Yep. Okay. Hello, I'm Yechul Shin, postdoc at Seoul National University at Korea. And as Sebastian said, nowadays I have a chance to visit and stay in the tomb to make interesting researches. And today I'd like to talk about early warning signal regarding AMOC tipping. Particularly, we're focusing on the reconciliation between observation and the model. Definitely, I can't do it alone. I mean, I got so much help from all my co-authors. So if there is something lacking in this presentation, that's on me. But any good parts are all thanks to them. And I'm really, really happy and honored to, give a talk in ClimTip webinar. So today we will deal with the Atlantic Meridional overturning circulation. I know you guys are much more better than me for this issue, but briefly talking about it is large-scale current system that transporting warm water northward in the upper ocean and the cold water at the southward at the depth. And the important thing is that it actually touches every corner of our planet. So these are just few examples, but if you see the northward transported warm water affecting sea ice variability, and it's the reason why we have a relatively moderate weather in the European continent. And also the nutrient and oxygen is accompanied, so that is a huge impact on marine ecosystem and the fisheries. And also the circulation itself affects the coastal sea level, so like every aspect, the AMOC affect in our planet. And I want to slightly emphasize this part. The AMOC is primary region. Why the intense tropical precipitation band? We call it intertropical convergence zone, located in the northern hemisphere climatologically. Like continent ocean distribution is actually not the primary region. The cross-equatorial energy transport by the AMOC is the primary region of the ITCG position climatologically. So AMOC is responsible basically in shaping tropical climate. So naturally, it affects to overall global climate system. So definitely one of the most important subsystem in our Earth. And the problem is that the AMOC is, I think it is formally classified as a tipping element. It means that if AMOC is abruptly changes, the propounding impact that I shown in before is actually potentially lead abrupt global climate responses. And these signals are actually recorded in paleoclimate proxy, which are one of the evidence we consider AMOC as a tipping element. And furthermore, even before we seen those paleoclimate proxies, the theoretical model, including Stoneman model, they already point out the possibility of AMOC's tipping the bistability. So which means that in our history, I mean, the long times ago, and also in our thinking, AMOC is considered as a tipping element. Then naturally, the consequences are about what about now and future? I mean, I'd like to translate in this way: could the global warming pushes the AMOC past its tipping point in our near future? And I think this is one of the most spotlighted questions in recent climate science society, particularly as these observation-based early warning signals are suggested. So here, these are two examples, but these studies utilizing fingerprint of AMOC, such as SST, sea surface temperature, or salinity composition, and suggesting that the current AMOC fingerprint or AMOC-related time series shares a statistical picture, which theoretically appears when bifurcation system approaches to a critical transition. I mean, here we have a typical pole bifurcation system. So as you can see, when the system is far from the threshold, the system have a higher resilience, high recovery rate, so its variance and autocorrelation is relatively small. But as a system gradually approaches to the threshold, I mean the bifurcation point, its rate of recovery gonna be continuously decreases, so that the stability is decreases, and it could be shown in measured, statistics such as variance and autocorrelation, lag one autocorrelation. So if we see like continuously increasing in these statistics, we said that, we report this phenomenon as a critical slowing down. And this critical slowing down actually applied in various studies to assess and identify the characteristic of our climate systems, and also in other studies. And at this step, I don't want to emphasize, overemphasize. Clearly, fingerprints are never perfect reconstruction, and CSD also cannot give a perfect alarm. We all know that CSD requires a lot of assumptions, mathematical, theoretical assumptions. So here, for instance, this figure, Wagner and Einsmann, which I like it, they show that in the simple energy balance model, they modulate Planck feedback, which is fundamental feedback related with the background temperature. And it's actually not that much related, not related with the tipping behavior. However, they can produce like spurious AR1 and various increases. So we always need to care about that. But however, I still want to suggest that like consistent identification of these statistics empirically grows a concern about our AMOC tipping in the future, because it's basically if AMOC collapse, we expect that there are going to be huge consequences. So I think this still makes sense. And however, this is me, and when I read those papers about critical slowing down, I just think really, I really not that much believe it. And at this point, I want to briefly talk about my personal introduction. So I'm basically studying climate dynamics, the atmospheric circulation, and most of my studies are focusing on how higher altitude climate change instigated the tropical circulation and tropical SSD pattern formulations. So these kind of studies are also also highly motivated from the paleoclimate proxies. So that what I want to say is that I also knew that those AMOC-related paleoclimate proxies, which is abruptly changes and the possibility of the tipping point. Nevertheless, I rarely care about that. Also my colleagues rarely care about it. The reason is that the general circulation model or system model, the modern climate model, generally does not show those kind of abrupt changes under global warming scenarios. So here I quote the IPCC report. So there is medium confidence that AMOC decline will not involve an abrupt collapse within this century. Actually, indeed, their previous report, AR5, they said that it was very unlikely. So if I a little bit exaggerate, they said that AMOC will not be abruptly collapse as much as sure the CO2 increases global mean temperature. But nowadays, they slightly modulate their tone about the possibility of abrupt collapse because they recognize the several ESM studies considering bias adjustment and parameter tuning, which actually produce some abrupt AMOC behavior, and they recognize it so that they reduce their tone. So very unlikely actually changes to medium confidence. So here, this stability bias known in the CMIM model, we will deal with it again in the later. However, but they still have a medium confidence. It's basically, if we see like multimodal mean AMOC times this, the projection, they are not showing that abrupt changes. So at this circumstance, we actually recognize that there is remain unclear whether the AMOC is too stable in those state-of-the-art climate models, or the fingerprint analysis are over-interpreted the likelihood of the AMOC transition. And I thought that it would be a really important question that we need to resolve it. Today I want to, I want to show some results that I try to resolve, not perfectly, but try to resolve these discrepancies. So in this study, we focus on the eastern subpolar North Atlantic region here, these yellow boxes, which is a gateway of North Atlantic current, warm salty water into the northern high latitude Atlantic Ocean, and also it pures the raw rim of the AMOC. And this region is, that's why this region is included in the majority of AMOC fingerprint, and there are several supporting lines that this eastern subpolar North Atlantic is highly related with the AMOC. But particularly, this region recently experienced a huge pressing event. So here, figure A, B, C shows upper ocean. Here, upper ocean means that surface to 200 meter integrated, salinity anomalies to their climatologists. And here we have a black boxes, and here figure D shows the annual mean time series of the upper ocean salinity for this region, eastern subpolar North Atlantic. As you can see, there is a huge present anomaly actually propagate into the eastern subpolar North Atlantic and then go into the Ermingus Sea and the Nordic Seas, which is also reported to reduce the convection in these regions. If you see the time series, there is clearly a huge dip in this pressing event. But furthermore, if we see those fluctuations, actually, they looks like continuously increases their fluctuation level. So like recap the critical slowing down and the loss of stability, I thought that it would be worth to try to analyze the critical slowing down for this region. So for better precision and long-term data set, we changes our target to the surface temperature and 4 different data set, HEDI-SST, COVID-2, ERSST, EM4, and calculating AR1 for 80-year window. Then, as you can see, since 1999, we see that AR1 increases in this time, in this region. I mean, I'm not saying that this is like, at this step, I don't want to like exaggerate that this is the like approaching to tipping point of AMOC, something like that. But at least we see those statistical signal in this eastern subpolar North Atlantic. And then we see a very similar and comparable signals in the climate model. So here I want to briefly talk about methodological things. So in this study, we utilize CSM2 large ensemble experiment for 50 ensemble member we use, and also for historical and the SSP scenario. So large ensemble, I think most of you guys are familiar, is basically conducted by repeating integration with same pulsing, but different initial conditions. So that their average is actually, removing out the internal variability, so that clearly shows the post response of the climate model. And if we remove the each time series from those post response, we can get a simply internal variability. So it's kind of experimental design that can enabling us to separation of internal variability and post response. And as you can see, for critical slowing down, we always calculate in the residual time series. So that I thought that large ensemble experiment is very suitable for approaching critical slowing down in terms of their design. Particularly, if we see previous studies, employing this critical slowing down, they actually usually make a test for its dependency on the choice of methodologies. For sliding window for calculating AR1 and the parameters for removing post response. And if you see here figure B or C, F, it actually the critical slowing down actually highly depending on the this post-response removing parameter rather than sliding window for AR1. However, in our study, because we employ large ensemble, we don't need to worry. We don't need to worry about the appropriate way to removing post-response. And of course, here critical slowing down and statistical signals that we shown in here is inconsistently, independent to the different window sizes, and also the characteristic of autocorrelated, characteristics of the noise. Here, Boetner and Bohr's 2022 suggest a very theoretical indicator that can avoid the misreading from the autocorrelated noise. And if we apply those methodology, we still have a very consistent critical slowing down in this Eastern Subpolar North Atlantic SST, both for observation and the model. So here, what I want to say is that, I mean, we cannot ignore the possibility of the false alarm and possibility of the methodologies, but it is true that we utilize as safely as possible to measure this CSD. Then let's come back to Eastern Subpolar North Atlantic critical slowing down. So this upper panel shows salinity anomaly, salinity time series. The middle panel shows SSD time series. In large ensemble, actually, we see that our inter-ensemble spread is actually increases under global warming scenario in this region. And particularly, it also accompanies with clear critical slowing down. I mean, AR1 increases in Eastern Subpolar North Atlantic. Here we not shown, but by Wavelet analysis, we checked that this AR1 increases highly accompanies with the decadal fluctuation, particularly for 5 to 50 year. So we tried to make a composite of the decadal salinity fluctuation in the large ensemble in between 2030 to 2060, which are shown in panel JKL. So this panel, JKL, the evolution of this decadal salinity fluctuation is, I think, qualitatively similar with what we recently observed in our near Earth. So here, we want to suggest that, at least in Eastern Subpolar North Atlantic, this statistical signal and accompanying spatial patterns are similar in between observation and the model. So if we consider it as a loss of stability, this similarity actually suggests that there is analogous underlying dynamics, maybe driving these two systems, statistical and spatial responses, which support us to compare observation and the large ensemble, although there is a lot of different parameterizations and grid configuration, but allow us to compare the observation and large ensemble in one plane. And then, but there is a remaining gap. So here, panel A shows both, Eastern Subpolar North Atlantic AR1, both observation and the large ensemble. Here, colors are observations and black is large ensembles. And here, there's two y-axes, have the same scale but slightly shifted. And we put the vertical dashed line here is CSD emergence, which is defined as years when each 50-year linear trend shows the largest changes, so which means that the point that it increases a lot. As you can see, it looks like similar, but CSD appears much more faster in the observation. We are about here, so it's already started. However, here, model shows a similar temporal evolution since 2040s. So actually, this timing gap is already somewhat comparable with the discrepancy what is shown in the introduction. So observation, fingerprint studies lean on the more considering risk of AMOC tipping, but the model-based projections are relatively, underestimate the risk of the tipping. And so we need to reconcile this gap. And if this critical slowing down is really reflect the AMOC's characteristics, AMOC's feature, and we thought that some AMOC specific characteristic would align with this timing differences. So we draw here panel B is AMOC strength at 2060 nodes. Here thick line is the reanalysis, and thin line is the large ensemble. And we also have a vertical dashed line to compare CSD emergence. And here, basically CSM2 do a good job in reproducing AMOC strength, which means that the AMOC strength in those CSD emergence time is not same. On the other hand, this shift in timing cannot be simply explained by some certain criteria of the AMOC strength, like 50 sweater would be tipping, something like that. So we turn on the AMOC stability. Yes, the study modulate the tones of IPCC report, which is shown in color here. Then as you can see here, blue lines with thick line and thin lines with black dashed line shows that very similar colors. I mean, which is suggesting that AMOC stability indicator is actually aligned with the Eastern Subpolar North Atlantic critical slowing down, both in observation and the model. So it's time to talk about AMOC stability a little bit more. Here we use the delta MOV, which is defined as a meridional overturning component of pressure convergence across the Atlantic basin. I use both southern boundary and northern boundary shown in this wrapped figure. So in these cases, if it is positive, which means that pressure is converged by AMO. So if AMO slowdowns, the convergence will be weakening, compensating the initial AMO slowdowns. On the other hand, if it changes its sign to negative, the pressure transport actually enhances the initial AMO changes, initial AMO slowdown, so that indicating self-sustaining feedback. So this kind of AMOC stability indicator is often adapted as a Bayesian scale sort of advection feedback, and also usually used for physical stability indicator for AMOC. And come back to those two studies. Here, Rio et al., they use the same metrics, delta MOV. And so here, basically make two climatologies, almost same climatological AMOC strength, but only different of the delta MOV. And then they put the same abrupt post-CO2 pulsing. Then, as you can see, the AMOV response is actually a lot amplified when we have a negative MOV. And this kind of stability indicator is partially suggested by Professor Ramsdorp in 1996 with only southern boundaries. Here, Van Westen et al. 2004, we all know this paper. It's like slowly, AMOC's abrupt change under slowly increasing pressure flux is actually reconciled with the southern boundary of the pressure transport by AMOC. But here we, some study use both and some study use only southern boundary, but in this study we use both cases to considering the convergence of the pressure transport by AMOC stream function. Then let's come back to the figure. So here we see basically similar critical slowing down in observation and the model. However, there is the only difference is the timing, and the timing looks like aligns with the AMOC stability indicator suggested by physical theory. So if we so here for black dashed line here we have 50 ensemble members, which is shown in here histogram in the inner plot. And if we put the ensemble mean of the observation and corresponding MOV at the ORAS 5, then their statistical significance is almost indistinguishable. So here I'd like to suggest that the statistical and critical slowing down based stability indicator, here AR1, is actually correspond well with the physical measure of the AMOC stability, both simulation and observation. So it actually supports that the Eastern Subpolar North Atlantic critical slowing down can be, reflect the loss of stability of the AMOC. And also, that's why we think that this significant critical slowing down in the observation is likely indicate some warning on our future. So one may ask that, I think it's a very natural question, but could the critical slowing down or MOV really indicate impending abrupt changes in the model? I mean, in the observation, if we can confirm this, which means that there's going to be a huge problem. However, for deal with this kind of question, we utilize the model and try to reconcile the model in the same framework. So to check this, to reply this question, we recap the characteristic of MOV. So here, basically, under global warming, AMOC is continuously weakening. And those circumstances, if MOV changes sign positive to negative, so what they explain is basically we will abruptly have a weakening of pressure convergence. The strengthening of pressure convergence, so that at least one site in the Atlantic basin, they're going to be abrupt increase of the pressure water, so that abrupt decrease in salinity and the density. So we check it. And then we found that the Nordic seas actually experienced some abrupt changes around with the delta MOV changes sign. So here panel B shows linear regression coefficient between upper ocean density and the AMOC for 20 years before delta MOV equals 0. And figure C shows the same one, but after delta MOV equals 0. And figure D is the ratio between these two. And as you can see, the sensitivity, density changing sensitivity to the AMOC is highly, highly amplified in this Eastern Southern North Atlantic and particularly Nordic Sea, like more than 6 times. So which means that in prior, like once bedrock decrease of AMOC with like 0.2 density changes, however, per year, but like after MOV equals 0, it's gonna be 6 times larger. So it's definitely something interesting. So we averaged this Nordic seas and plotting its time series and AR1 in panel A. And for panel E, this is actually decadal averaged vertical profile of the Nordic seas, but each color is corresponding to the delta MOV. So if we see the Nordic sea density actually shows some abrupt changes, particularly around 2060s, and this critical slowing down also consistently shown in 2030s. If we move on the density profile, here actually in blue colors, here there is a lot of lines because historical is like 150 years in every ensemble members. However, this density profile change is actually accelerated when the delta MOV reduced as much as green color, which actually we see the CSD emergence consistently in the observation and the simulation. And then the stratification actually going to be severe as MOV decreases further. Here, this kind of density profile clearly indicate that the overall increase in stratification, so implying contraction of the dewater formation in this region. And this figure can be repeated in the salinity, and basically they are very similar, suggesting that because delta MOV is, relating with the pressure transport, so that those kind of density responses are driven by salinity, not the temperature. So it's also consistent with what they're thinking about. So until now, we kept the findings. We first suggest that there is consistent statistical and critical slowing down in both observation and the model in the Eastern Southern North Atlantic. And second one is that although they are overall similar, there's a timing difference, shift in critical slowing down timing, and we explained it. It can be reconciled by the physical AMOC stability indicator. And third, in the model, we actually see that those kind of critical slowing down and the MOV decreases are prior to the overall stratification in the deep convection region in the North Atlantic. And finally, we make a scatter plot between this delta MOV and here critical slowing down, AR1 in the Eastern Southern North Atlantic. Together with observation and the model, here black dots and black lines are the Raji ensembles. And each colors indicated each observation data set. And we put the linear fitting for each one. And again, here we have a blue thick shade line because each data set have a different ranks of the point. We averaged the fitting of the each ensemble member, not ensemble, and then make a fitting. But I think it's basically very similar. Then here, this is basically how physical stability and statistical stability relationship shown in observation and the model. And basically, those are highly similar. Here, model's AR1 is slightly higher than observation's AR1, but I thought that there are going to be bunch of regions that the amplitude can be different, like coarse resolution in the model, maybe problem in the parameterization, crude physical processes, maybe in observation, some errors. However, it is still very surprising that overall trend is closely aligned with the MOV and AR1 space in between observation and the large ensemble, at least this available observational period. And I want to note that this physical statistical stability relationship is somewhat consistent. Somewhat consistent in the also CSM1. Here, blue colors I use a 28 1% CO2 experiment driven by CSM1, and black one is again CSM2 large ensemble. And here we put the linear regression and their statistical significance range, and they are basically comparable. So we know that, CSM1 is another, not a different model. it's different, but not totally different. It's rather different generation of the model. However, I thought that this kind of consistency still, relieves our concern about the different model configurations. So come back to MOV and AR1 space. We observed that MOV is actually continuously decreasing, which is consistently shown in the Rene van Westen, although he used only southern boundary. I thought it's overall going to be similar. So here, and recently, the value reaches nearly zero. In the model, we actually see abrupt collapse happen in the Nordic Sea convection. I don't expect, I don't want to say that we are just imminent of the what we've seen in the model, but this kind of result still suggests that the observed AMOC is actually looks like losing a stability, so that increasing the probability of a tipping point by using our model experiment as a benchmark. And then we can change our x-axis using x-axis, control parameter to user criteria to assess the risk of the tipping. Global mean temperature. Here I use actually global mean SSTs. I just want to use that only for the ocean, but maybe I need to change it. But it's basically very similar. However, if we change our control parameter to the stability to the temperature, as we can expect it, the stability response is no longer agrees between observation and the model. Rather, here observed CSD is as severe as that simulated in the large ensemble only after global mean temperature has risen by 1.5 Kelvin. So for global mean surface temperature, I'm sure that is already far exceeding the Paris Agreement target. And we note that not only CSM2 here, the boxes are general CMIP range of the delta MOV, and each dots are here, particularly these dots, circles are observations shown in Liu et al. 2017. We know that overall Earth system models nowadays, Earth system models have a general bias in reading this kind of underestimation of the proximity of the loss of stability in simulations. So I thought that our finding is basically suggest that we try to tend to support the overlooked warning in the biased ESM rather than overinterpreted warning from the fingerprint analysis. So this is my summary. I just tried to summarize some controversial argument based on my knowledge. So it's and maybe not perfect, but we start from the early warning signal in the observation-based fingerprint, maybe one that tipping point is approaching. However, there is argument that a fingerprint can be, uncertain, and also there are going to be false alarm. And they said that, GCM there's no abrupt collapse. So there, we are not sure about the, AMOC tipping point. However, the papers that I shown, they suggest that the current climate models generally suffer to the stability bias. And if we appropriately handle it, then there are going to be some abrupt transitions. But clearly, I want to say that this kind of stability argument yet fully explained intermodal spread, I think. And here, if we apply our result, so first of all, we at least see coherent signal, both in model and observations. So I think relatively we are free for the fingerprint errors. And also we just use the regional SSTs that is highly related with the AMOC. And second one is that here they said that most of GCM does not project abrupt AMOC collapse before 2100. However, in our result, we show the possibility that those stability biases, because it actually rely on the stability response both in observation and the model. So we try to tend to support this kind of bias maybe substantially hide and overlooked the warning in our current, climate change. And finally, I think I want to talk about this one. It's somewhat related with my issue. So it's basically I make a two simple gradual and critical system and putting very abrupt increase of the pulsing and slowly decreases pulsing. So it's actually what we think about it's going to be our future, right? If we consider this pulsing as a carbon dioxide. Then here, there are going to be not that much abrupt changes, both in gradual and critical system. However, because here, if we are red, not the blue, we already, at this point, we already, move into alternative stable state. But here we are already state in this, AMOC state, so that the linear, the pulsing mitigation effort actually does not simply reproduce in the AMOC recovery, so that the profound impact that we've seen at the beginning still would have a influence in our society. Of course, if we I guess about here, the AMOC gonna be recovery, but the recovery also very fast. They're also gonna be problem of our system and our Earth. So I want to say that it's when we considering AMOC collapse and its system, warning of a tipping point, I thought it is a little bit better to consider the stability, how system going to be changes, and the system is really considering tipping-like behavior rather than just the abruptness of the collapse, because we guess that our anthropogenic pulsing is already maybe too fast. Thank you for your time, and thank you for listening. I'm done.
Thank you so much, Yechul. Thank you for your super interesting presentation. I was wondering if we have questions from people who joined us. I wanted just to clarify, Yechul, on the last slide, when you say the loss of stability, is there something missing? The loss of stability, I'm understanding, is it more abrupt than the abrupt collapse, or more important?
So if our pulsing is already too fast, then there are gonna be not that much shown in abrupt acceleration in AMOC weakening. So both system is not exactly the same, but both are looks like collapse. They are substantially weakened. However, the response to mitigation, response to the reduced pulsing is totally different. So that not appearing abrupt acceleration in AMOC time series might not perfect, depends on our concern on tipping point or AMOC tipping characteristics. Because after that, our mitigation period, those gonna be huge problem. It's just based on my thinking.
Right. Thank you. Yeah. Please go ahead. You can unmute yourself and ask your question. Sibrin?
Yes, I'm Sibrin Drijfout from a few other European projects on tipping. Yeah, Yechul, thank you for the nice talk. There was one thing not clear to me. So in the beginning, you showed the time series for, I think, SST and SSS, so surface salinity and surface temperature, in this box, and showed that they both showed CSD. And I thought, or I would think that SSS would be a cleaner signal than SST, but afterwards, I think you showed all the AR1 diagnostics based on SST. So why did you choose SST over SSS? And and do you feel that that is a better one, or is it the other way around? But because of a more unsure observations, you choose to stick with SST, because SST will also be influenced by global warming, I would think. So that is always a metal signature.
Yeah, I mean, that's definitely a very fair question. So I did not include the salinity response. So first of all, if I calculate the salinity AR1 in observation and the Raja ensemble, there is a somewhat consistent part and inconsistent part. So overall, the like evolution and the time series looks like a similar, but for me, this part, the AR1 in the model and the observation is totally different. Here, we actually have a comparable level, but salinity is not that much consistent. So I thought that it's maybe better to utilize SST data set. First of all, they are a lot, like more than 100 years salinity time series, including the depth until 200 meters only, limited in the EM4, but for SST, we have allotted. And then for this Eastern Subpolar North Atlantic, I thought that the North Atlantic current highly determine the seawater property in this region. So I, actually try to translate in the SSTs. And you concerned about the global warming signal, but we actually, so in the Raja ensemble, we have a like relatively perfect method that we can remove the post response. And here observation, we don't have it. So what I try is like this way. So here, I actually try in my Raja ensemble for different window to remove the post response, and we actually choose the most well-fitted correlation coefficient and large ensemble. I mean smaller RMSE. So if you see AR1 from ensemble removed and trend removed, we can have a relatively comparable result. And we apply this method into the observational AR1 calculation. So I think that relatively we are not that much worrying about the global mean signal because we already remove it.
Okay.
Yeah, thanks.
We have Stefan Ramsdorf. Please.
Yes, hi. Thank you very much for a very interesting talk. I have two questions. The first one, would you summarize your result that certainly compared to that model ensemble that you used, the model is lagging like 50 years behind compared to what the observational data suggests in terms of proximity to the tipping point? And then my second question is just your publication plans for this, whether you've already submitted, etc.
Yeah, thank you for question. So, so here, yeah. So you mean that how I estimate the proximity between, I mean, underestimation of the proximity between observation and the model based on this kind of figure, right? I think it's right. Yeah. So here in the panel A, we have a relatively consistent the physical stability and statistical measure of the stability and those are consistently shown in both observation and the model. So we think that here, we assume that if our future looks like the CSM2, that is actually what we can do for our future, because we cannot project without a model. So then we can actually compare how our current critical slowing down looks like, which period in the global warming simulation, the CSM2, based on the stability MOV that was just suggested. And then go to the next figure, panel B. It's just same figure, everything same, changing x-axis to the SST. So here SST is for me is kind of time frame because observation and CSM2, their global mean SST, global mean warming is basically very similar. So this is basically time. And then here vertical line, dashed line is for observation, the last MOV in ORAS 5. And here blank line is the same value for this dashed line. And if we compare these two dashed line is about 1.5K warming. On the other hand, currently, with respect to the temperature increases, I mean, under global warming, we have like this kind of severe increases in critical slowing down. So if we assume that this CFD is actually reflecting this stability, then we have like this kind of severe stability decreases. And we see those comparable trend of the decreasing, stability only after, substantial warming happens. And if we compare only the endpoint, I guess they're like maybe 1.5K. I mean, here 1.5K is actually not that much important, but important thing is that the model's stability biases actually make a misreading if we using like global mean SST as a criteria for tipping dynamics. Yeah, and I submitted into the science, and I'm waiting for the editor's decision. Yeah, hope, finger crossed.
Yeah, thanks. Good luck with the
Thank you.
application. Very interesting result.
Yeah.
I was wondering if you have any more questions. Oh, it looks like a whole group watching us from Danish Meteorological Institute in an audience. Okay. Sebastian, please go ahead.
Yeah, thanks. The slide you discussed with Cyprian before, you showed this event. Yeah. So can you explain again what the link is, the connection between this event you show, for example, on the maps on the left side, observations? There's the density anomaly, and you show how it spreads over time in this specific case, and something like that it happens in the model. And if I understood correctly, you show this to justify your choice of the region, right? To define the fingerprints. Because through this region, the anomaly that passes there by advection, it ends up in these convection sites. Is this the argument?
So if I understood correctly, first of all, the reason why I choose this site is, first of all, there is something huge fluctuation is reported in recent days. And also at the same time, this site there is several evidence that it is highly linked with the AMOC strength. I'm not sure I can say that, but like, Shimon Michel's preprint, we knew that they also have a higher, heat map in those eastern North Atlantic. And considering the climatological current, I thought it's still worth to consider this, near Irming Sea or Lac Trope regions. And your first question is comparing these three panels with JKL, right? Right, okay. So what I do is that here, this is actually one event that we've seen and looks like relating with the increasing AR1 in the eastern North Atlantic. And we have a similar AR1 increases in this time period. So we actually want to capture how this AR1 actually looks like in their spatial pattern. So what we do is firstly calculating here. This is calculating wavelet analysis for eastern North Atlantic SST. So this is I first calculated wavelet map for every ensemble and then make it composite. So here, these yellows are actually saying that in terms of ensemble mean, their wavelength increases, which is particularly for about 10 period for 2030 to 2060, where AR increases most significantly. So I thought that this is basically a decadal fluctuation. And here was, no, sorry, salinity for is 5 to 10, but it's still comparable. So this is the salinity time series removing the, trend. And we see that the fluctuation actually increases around 2030 to 2060. And here, dashed line is the 3 standard deviation of the historical period. So in future, it's going to be actually in historical, it is very rare event. And then we actually capture all the events that the salinity fluctuation exceeds 3 standard deviation of the historical, and we gather it together, make it composite based on its minimum salinity at the eastern subpolar South Atlantic, and then making those time periods to showing how salinity anomaly looks like before that year and after that year. Then, which is resulting in JKL, and it is not exactly the same, but overall, here it's like the salinity anomaly in this North Atlantic current and moving on to the Omega Sea and actually propagating to the both way. Overall, I thought that it's similar. So these are also, for me, it's kind of supporting line to these two CSD is comparable, although it's not same.
On the right side, the 3 maps is a composite from the model.
Yeah, right.
Okay, cool. Thanks. More questions?
And maybe just one quick question, Yechul. To what extent do you think does this depend on CSM2? Because all the different models have different biases, and the question is, to what extent could this be made? Could the results change or made more robust if you look at different models and basically then try to remove the model biases?
Yeah, I mean, so first of all, this is the current figure that I only can show you. It's like, for instance, like CSM1 and 2, the trend looks like comparable. So, and I think I will also try to like different model ensemble, large ensembles, particularly because it's very suitable for removing positive responses. And then your later part is about the removing biases in MOB, you mean, right? Yeah, I mean, for me, it's like, frankly speaking, I think that if it was easy, that's gonna be already done. I mean, I guess that if we try to removing those, because those, here, what is shown is that this stability bias is basically linked with the fluctuation level of the AMOC and AMOC related SSTs. So if we change it, I'm 100% sure that all the climate variability is going to be changes. So the model may not work to use as a future projection model. So for those kind of things, I thought that it's maybe better to approach in like detouring. I mean, finding a detouring way to utilizing this information to modeling things, I guess. Yeah.
That makes perfect sense. Thank you.
Yeah. Hello.
We have another question from DMI.
Yeah, thank you. Can you hear me? I'm Stefan Olsen from DMI.
We can hear you.
Okay, thank you. Yeah, thank you for a very nice presentation and a lot of interesting points. One question to the critical slowdown signatures of the subpolar North Atlantic plots. It's a region with a lot of variability. You basically have a couple of major events in your record here on your maps to the left. How do these individual events with kind of decadal scale features influence this increase in your critical slowdown statistics? Have you tried somehow to test that significance? And kind of a parallel question is, we see this variability in your SST record, but we also know that the actually observed strength of the AMOC in that region has been stable from the 90s and onwards. So there's no one-to-one relation between SST and AMOC strengths.
Yeah, that's also very fair, nice, and critical questions. So, so for me, first of all, I also agree that so here we actually compare fingerprint and the model. And the reason why you utilize fingerprint, I mean, not you, I mean, us exactly, but in previous studies talking about, AMOC critical slowing down is the critical slowing down always needs a sufficient time scale and sufficient data set with appropriately removing positive response. So I agree that like very precise observations on different water mass which are actually not that much new, but those are actually not showing substantial decreases. So I think that even in observation fingerprint and the reconstruction and the direct measurement, there is a discrepancy that we need to see further. And second one is that you said that here, this is basically one part of variability and how it can connect it to the, AR1, right? Am I right?
Sorry. As I was pointing to the link between the SST index and known strengths of the AMOC in that region. I think it's more or less clear that we have had a stable AMOC, partly increasing through the 90s and to present. So I don't see these large fluctuations that you have in your SST record reflected in observed strengths in the AMOC at this latitude.
I think that, so I think that's a good question. I think it's worth to check it. But here, as you said, that here SST is basically containing a lot of the wind-driven variability, the past frequency, so that here SST itself may not highly coupled in terms of the AMOC stream function or AMOC observations with their overall variability. I agree that. So in terms of that, I think I acknowledge that they're going to be misreading. But here is, it's kind of, for me, it's like alternative chosen that if we want to see some stability. It looks like too detouring, but to see those kind of long-term changes and sufficient data set to see the stability or related statistics, I thought there's still surface temperature that is known or we can link to the AMOC's picture is the one of the best choice. It's like if we have a rapid MOC array for like 50 years, then we definitely already people publish the paper about its stability changes, but actually not. So that's why we unnecessarily, that's why, although we don't want to, we used to like observational long-term record to, avoid the reg of the data set. But I agree that those kind of observation, direct oceanic observation and this kind of SSTs should have a gap. So we need to always carefully interpret this statistical result. Thank you for your question. That was great.
Thank you for all the perspectives here.
I was wondering if I could ask maybe one question quickly. In the beginning, you had a slide on the comparing the statements about AR5 very unlikely to AR6 medium. So just on a as a summary to what this results that you find show, where does it move this study, right? The dial from AR5 to AR6 in terms of confidence of the statement there on the collapse of AMOC before 2100.
Okay. So frankly speaking, in terms of this, just this argument that AMOC decline will not involve an abrupt collapse, I think it would be still make sense, even my results are all true. However, my concern is that if we have a substantial changes in thermohaline structure of the Atlantic Meridional overturning circulation, though we haven't checked like modeling additional experiment that there is really not recovery or not, I think like this kind of situation would be more preferable because we have a very strong CO2 forcing. I guess whatever the model, even if it's tipping or not, AMOC gonna be decreases a lot. It is clear. However, after we try to mitigate, the AMOC response gonna be highly different. If it, based on its characteristic. If it is really tipping element, then it's gonna be something different. Particularly under like within this century, if our pulsing is passed over the tipping point, then like the weakened state gonna be stayed unless we really reduce CO2 actively. However, if our system is just a linear system, it's like there's no abrupt class, then it's not actually meaning the loss of stability and transition to alternative state, then we're gonna be simply recover if we reduce the pulsing. I mean, as much as we reduce the pulsing, AMOC gonna be recovered. Of course, there are gonna be some inertia impact or also like impact, but the recovery would be fine. So in terms of that, I think that we looks like the signals relating with the AMOC stability loss. So which means that our system looks like more than red one rather than blue one. I mean, of course, we also have an abrupt collapse because our current model have a biases that have a postponing the known critical slowing down in the observation and the model. So yeah, that's gonna be my
Thank you.
remark. Yeah.
Thank you for your summary, and thank you for your really interesting presentation. Thanks everyone for participating.
Thank you for all guys. Thank you.